Justin Eckert, Biosystems Engineering, Integration Lead.
Mark He, Mechanical Engineering, Simulations Lead.
Raul Hernandez, Mechanical Engineering, Mechanical Lead.
Isabel Scott, Mechanical Engineering Team Lead.
Frank Thursto, Electrical and Computer Engineering, Electrical Lead.
Will Gillespie, Engineering Management, Procurement Lead.
Our project is part of the Biosphere 2 Big Idea Challenge. We are not just theorizing, but combining real-world experiments with simulations to predict what happens over time. The long-term goal is to help build a national center focused on terraforming and making environments more habitable both in space and here on Earth. We have designed and built a high-fidelity environmental chamber to replicate Martian conditions. This includes controlled systems for temperature, lighting, and irrigation, along with sensor packages to monitor environmental data. We want to highlight two key concepts used in our project. Terraforming is the process of transforming a planet to make it more Earth-like and habitable. Leaching is when water moves through soil, carrying dissolved nutrients or salts with it. Perchlorites, found in Martian soil, is a major challenge as they are toxic salts that interfere with human health and prevent plants from growing. Our goal is to remove and reduce these chemicals through leaching so the soil becomes safer for agriculture and long-term human use.
Our system requirements have undergone multiple iterations from September through February as the active research team has further developed their experimental needs. Firstly, we're creating the ambient environment of the chamber to simulate select Martian conditions. Our group is responsible for creating a sealed chamber that can set and maintain target experimental air, a set temperature range, and control humidity. Our group is also connecting all of our equipment through LabVIEW. This includes real-time logging of ambient conditions of chamber temperature, relative humidity, and flow rates at different points of our irrigation system. Within the soil column subsystem, we are monitoring temperature, water potential, soil moisture, and allowing for water sampling at different soil depths. Data points will be saved and stored from each sensor every 5 minutes. All water will be collected for further analysis. Finally, we have continued design requirements, such as minimum 5 columns, levels of soil and gravel, applied water amount per irrigation event, full spectrum lighting, etc. All these requirements ensure the system can provide accurate, repeatable conditions for long-duration experiments.
This is our system block diagram, which key components will be highlighted in the next part of the video.
All right, so here you can see the chamber more or less assembled with all the subsystems put together. So here you can see the cable glands. These are what the electrical and water pass-throughs to get to the inside of the chamber are going to go through. You have the acrylic panels themselves. These are 1/4 inch and they're adhered to an aluminum frame. These aluminum frames are made of hollow aluminum stock in order to reinforce the structure, and they're adhered with steel epoxy. Coming into the back, you can see the gas system. This is what actually creates the Martian or experimental atmosphere. So you have just a standard air hose that's connected to a bulkhead with a check valve. This hose will connect to the mass flow controller and then be connected to the gas tank itself. You can't see it, but on top there are 2 bulkheads that look just like this. They're connected to ball valves on the exit. So what happens is the air comes in through this inlet and then it just basically pushes air out the top. And then finally coming in on the other side. So here you can see some of the pre-NART electrical and water cables passing through the gland itself. We're missing the gland on this end, but we're going to get that one filled in shortly. And then basically, this is what it's going to look like in operation. So you have all these cables connecting it to the power source, as well as the water connected to the pump, getting our samples from the soil columns.
So talking a little bit about our soil column configuration, right here we have our 18-inch tall soil column placed on top of our load cell, which will measure how much water we have inside of it. Then we have our drainage water adapter, which will allow the drainage to pass through. We have our mesh tied onto it with a clamp. We have our irrigation system, which will be connected to the pump. And the soil columns are separated at 4 inches tall. So we have 3 inches of gravel, 12 inches of soil, and these soil column packages are separated at 4 inches each.
So this is the irrigation system into the soil column and the drainage system. So here we have our irrigation pump. This is actually a diaphragm pump, which is used for chemical injection into other processes that we're using as an irrigation pump for this project. On this line here, we have the infill water, the source water will pump in through here. The source water will follow this 1/4 inch inside diameter tubing through this barb into the irrigation hub, which has 6 ports, 5 of which are used for each of our soil columns. A certain height of water is going to be applied to this, and then it's going to percolate through the soil layer, which is going to leach or dissolve the perchlorate electrolyte and run out through the drainage adapter.
This is our electrical cabinet, where all sensing signals come in and all control signals go out. Here's our most important sensor. It measures temperature and humidity. Using the data we record from this sensor, we can make decisions regarding the atmospheric controls in the chamber. That's the humidifier, dehumidifier, and the thermoelectric heaters and coolers. Those controls all get processed through this relay, turns them off and on. Additionally, we take in signals from the sensors embedded in the soil columns.
With the complexity of our project and its evolving requirements, our verifications have been extensive, and all requirements were put through repeated verification upon final integration of the project. We focused heavily on quantitative testing to ensure our design met all performance requirements. We conducted extensive testing to validate temperature control within plus or minus 2 degrees Celsius and confirm stable atmospheric conditions over time. Irrigation testing measured water application per event, where we did achieve an average of 1.7 centimeters, well within the required 1 to 10 centimeter range. We also performed drainage testing, collecting 72 milliliters of effluent, exceeding the minimum 50 milliliter requirement. For data acquisition, we verified all system parameters, including temperature, humidity, and flow rate, were consistently logged at 5-minute intervals. Additionally, soil monitoring tests confirmed continuous temperature readings at both 4 and 8 inches below the surface, and full sensor package testing verified accurate logging of soil moisture, temperature, and water potential within our soil columns. Overall, these tests demonstrated our system met key performance requirements through repeatable, data-driven validation.
All subsystems have been designed and constructed. The chamber frame has been pressure tested to withstand 5 times normal operating pressure. The pedestal fully supports the chamber, and the irrigation system has been implemented to provide consistent flow for effective leaching. From this project, we learned that environmental control is highly sensitive, especially with sensor placement and sealing, and even small leaks can impact stability. We also saw strong interactions between temperature, humidity, and gas levels, making early testing and data logging critical. Moving forward, we plan to test with higher CO2 concentrations, explore new soils with leaching techniques, and introduce seeds to study plant growth after leaching.